Good morning. Up until now, we've looked at discrete probability distributions. However, now we're going to change things up a little bit and start looking at continuous probability distributions. And in this world, the outcome space or sample space is continuous. And things can get a little bit weird here. So let's start with an example to see what's going on. Let's say we have the interval 0 to 10. And you throw a dart at this interval. Let's assume that this dart has an infinitesimally thin point and that every point between 0 and 10 is equally likely. So I have a couple of questions. What's the probability that the dart lies in 4 to 5, somewhere in that interval? What's the probability that the dart hits exactly x equals 4? And what's the probability that the dart lies in 4, 5, where I now have an open interval? So pause the video, use your intuition to try to solve this, and then after you're done thinking about it, press play. All right, so hopefully you said, well, I don't know, the length of this interval is 10, the length of this guy is 1, so 1 out of 10. So again, I'm using my intuition here. I'm not really, I don't have any sort of formal mathematical formula behind the scenes. Another way that you could have thought about this is just think of it in terms of relative frequency approach. And if you do this again and again and again and again and again and again, since that length is 10, since that length is 1, about 1 out of 10 times as you proceed out into infinity, it's going to be in this interval. What about the probability that x hits exactly 4? Well, if we think of this again in terms of the relative frequency approach, we're going to get a weird answer. And that answer is 0. Because if I count the number of times that I exactly hit 4, divided by the total number of trials that I'm doing, and I take the limit as n goes to infinity, well, that ratio is going to get closer and closer to 0. So the weird thing about this is that this can happen, but we say it has a probability of 0. With that in mind, another weird thing is that this probability and this probability are exactly the same because they just differ by 1 point. And the probability of that particular point is 0. In fact, another weird thing is if I subtract or take out 1 million, 1 billion, or 1 trillion points from this, I'm still going to get 1/10 as the same probability. Okay, so let's now formalize this idea with the concept of a PDF. So a PDF, this is a probability density function, is an integrable function such that 1, f of x is bigger than 0. 2, if I integrate over the sample space, I get 1. And 3, probability that x is within some set A is going to be equal to the integral over that subset. Okay, so let's look at this. So it's called the probability density function. So before we call them probability mass functions, the PMF is the world of discrete, the PDF is the world of continuous. It's integrable. I don't want to get bogged down in the formal definition of integrable, but let's just say we can integrate the thing. It's positive. If I integrate over the entire sample space, I'm going to get 1. So this might be new notation for you. Typically in integration class in Calc 2 at Western, you would see something like, from 0 to 5. But another way of articulating 0 to 5 is you could write it like this. Just put it down here. You could write something like this. X is contained in 0, 5. Or you could write it like this down here. And we're going to do it like this because this makes it so that our set that we're integrating over doesn't just have to be from 0 to 5. It could be, for example, from 0 to 5, union from 10 to 20. So that gives us a little bit more flexibility. And we're also saying that the probability of a particular event is found by integrating it. So pause the video for a second and think about what the implication is in terms of geometry and probability and integration. Well, hopefully you said that since this is equal to this, and we know that f of x is positive, that the area under the curve f of x is the same thing as the probability. The area is the probability. Okay, so that makes this guy make more sense. We're going to dig into this particular example a little bit later, but let me just say, what's the area under 4? Whatever the curve happens to be. I haven't even articulated what f of x is, but if I'm just integrating from the point 4 to 4, then I get 0. So that makes sense. Okay, so we have some more definitions. And these are all straight analogies from the discrete case. So if I want to find the expected value, I just integrate over the sample space x times little f of x. So instead of summing, I am integrating. Let me just say another way, and I'm probably going to typically write it this way, is to express this as the integral from negative infinity to infinity. Now that might seem a little bit scarier, but basically what's going to happen is that our PDF f of x, it's going to be 0 a lot of the times on a whole chunk of the real line. So this negative infinity to infinity is actually going to turn into something like 0 to 4 as an example. Because outside of 0 to 4, this is going to be 0, so that becomes 0 as well. The variance of x is defined in the same way as it is in this discrete case. Whoops, left out an important piece there. Okay, in the discrete case, it was the sum, x minus b squared times f of x dx. I'm going to leave this as an exercise to you guys. Feel free to ask about it if you weren't successful. But if you square this out, separate out the integrals, just like you did the sums, you are going to get the exact same fun formula that we got in the discrete case, which is that the variance is the expected value of x squared minus the expected value of x squared. All right, so in deriving PMFs, what we did is we looked at the probabilistic situation, we did a couple of examples for specific points, and then we developed the general formula. We can't do that here because the probability of any particular point is 0. So we need another approach to come up with the PDF. We need a different approach. So what we're going to do is, it's something that's going to seem a little bit weird first, but you'll see why we're doing it in a minute. So to find a PDF, one way we can do it is we can first find what's called the Cdf. And this is the cumulative distribution function. The cumulative distribution function. And the name describes exactly what it is. So this guy is a capital F of x, and it is defined as the probability that a random variable, is less than or equal to a particular x. So, for example, big F of 2 is the probability that x is less than or equal to 2. So, why is that helpful? So, first off, hopefully I can come up with this thing because, again, it's continuous. So I'm going to start thinking about the probability over an area, which I'm hoping I'm able to do. But why is this helpful? Well, this guy is then the integral from minus infinity to x, right? We're going to a specific x. We're going to integrate our PDF, which we actually don't know at this moment, to get this guy. So why is that? Well, let's look at a picture. So let's say my let's say this happens to be my PDF. So it happens to be 0 over here, and it's a decreasing function there. So if I integrate from negative infinity to a particular x, well, aren't I getting the area under the curve to the left of this? Yeah, I am. So this is why this is this guy. It's the same thing as the probability that big X is less than or equal to x. Students always ask, hey, how come you have this t in here? Well, because this x is representing a fixed value x here. So I can't have x's here and x's here because these x's are representing that limit involved in computing integration. Okay, so big F of x is this thing, but that means that big F prime of x, the derivative of this cumulative distribution, is, pause the video and see if you can answer that question. Hint, it's from integral calculus. It's from a theorem that you thought you would never ever use ever. Well, hopefully you said, oh, yeah, I remember this. Big F prime of x is just little f of x. That's from FTOC Part 2. Now, if you didn't remember that, don't feel bad. All kidding aside, I have about 1 out of 40 or 50 students who remember that. Okay, so you might need to recheck that out from a calc book. Okay, so then if we can find this guy, then we can find this guy by taking its derivative. And here's what we're going to do. This guy is this, and it's also this. What we're going to do is we're going to come up with this without thinking of it as an integral. You'll see it when I do an example. We're going to be sneaky about how we think about this, but we know it is this, so it doesn't matter if we don't know f of t. We know that this is the same as this, and whatever we get for this, we know that we could just take its derivative, and out will pop little f of x. Okay, and you'll see that in an example. So again, the point of this is we can't actually compute, well, we can compute the probability of a single point, but we're always going to get 0, so that's kind of a waste of time. So that's why Cdfs are powerful. Let me show you why else they're powerful. If I want the probability that my random variable is between 2 points, so it's on that interval, then I can integrate from a to b f of x dx. Well, that's the same thing as the integral from minus infinity to b of f of x dx minus the integral from minus infinity to a of f of x dx. Let me show you that with a picture. So, let me just use this guy here. So, no, it's too messy over there, too messy. So let's say we have a particular f of x. I'm going to draw a different one that we'll see a little bit later. So this is f of x. It happens to be constant and then 0 outside of that interval. If I want the probability of being between here and here, so again, that's just going to be the area. So can I just take all the area to the left of B and subtract all of the area to the left of A, right? That'll give me the stuff in the middle. Well, by definition, that is big F of B minus big F of A. So if you can come up with your big F of X function, then you have a shortcut to computing this probability. In other words, you won't have to integrate. You'll have some function big F of X, and you could just plug in B, and you could just plug in A. All right, so we need a concrete example of this. Let me just say that this section is historically tough. This was tough for me when I was a student, I remember. This is just weird over here. So you're going to need to sit with that concept. Don't just memorize the formula. You need to sit with the concept and keep reminding yourself of what that means. But let's do a concrete example so we can see the CDF in action. Okay, so let's say we pick a point at random from the interval 2 to 5. Okay, so same game, points are equally likely. It's just like the dart example that I gave at the beginning. I'm going to ask, what's the probability that x is less than 4? Okay, so give that a shot. Give that a shot. Well, hopefully you said 2/3. Now, why would it be 2/3? Well, let's see, 4 is over here. The total length is 5 minus 2. And the length that I'm interested in is 4 minus 2. So we subtract those guys and we get 2/3. And note, we actually just computed a value on this functions, which we haven't defined yet. We just computed the value on the CDF. Now I know I said before it's the probability that x is less than or equal to x, but I also said that the probability that x is a single point is 0. So whether I write less than or equal to won't make a difference. So let's talk about this situation in general. So in general, let's let x be the result of randomly picking a point on an interval, a to b, where a is less than b, and each point is equally likely. So my goal right now is to come up with the CDF, and then from the CDF I'll take its derivative, and then I will derive the PDF. So first the CDF. Let me write it over here so we can see what we did over here. So we want the probability that x is less than or equal to x. And our interval, again, is now from A to B. So this guy here is x. So we actually have to case this out. In case 1, x is less than A. It's in this interval here. In case 2, x is contained in the interval A to B. And in case 3, x is bigger than b. You'll see why we need to case it out in just a second. But the one that we looked at already, see if you can come up with the middle guy based on what we did there. Right, hopefully you said that's going to be A. No, hopefully you said it. Hopefully you didn't say that. Hopefully you said it's going to be x minus A over b minus A. Right, b minus A, x minus A. So that's the middle guy. Well, what if x is less than A? If x is less than A, what's the probability that x is less than or equal to some number less than a? Hopefully you said, well, that's 0, because nobody's home over here. We're picking a number between 2 and 5, so what's the probability that x is less than or equal to 1? That's 0. What's the probability that x is bigger? What's the probability that x is less than or equal to some number that's bigger than b? What's the probability that x is less than or equal to some number out here? Pause the video, think about it. All right, this one's a little bit trickier. A lot of people say 0, but it's not 0, it's actually 1. Right? The probability of being less than or equal to some number out here, like 6, is 1 because all the numbers are between 0 and 5. I'm sorry, all the numbers between 2 and 5 here. So this is the CDF. Notice we came up with the CDF without integrating anything. However, now that we have the CDF, we know that the PDF is just the derivative of this guy. Derivative of 0 is 0. The derivative of 1 is 0. So we just have to look at this interval. It's going to be something if x is there and 0 otherwise. So pause the video, see if you can take the derivative of x minus a over b minus a. This historically has given my 341 students some grief, so give it a shot. All right, probably it's tricky because we have all these letters here. Probably the easiest way to see this is if I break it into 2 fractions, and then I see the first guy is this. Okay, so now let me take the derivative of this. Well, this is just a linear function. Derivative of this is 0. The derivative of this is just the slope. So we get 1 over b minus a. And that's it. Okay, so this is called the uniform distribution. So in this case, x is uniform over the interval a, b. Now, let me point out that we had a uniform distribution already where we were given just one parameter, m, and that was the discrete case going from 1 to m. When you see a comma b, this is telling you that it is the continuous analog of that. Right, so let's play around with this a little bit more. Let's try to find its expected value. Well, the expected value of x, by definition, is the integral over the sample space, which is a to b, of x times f of x. And f of x in this case is 1 over b minus a. Before we work that out, what do you think the expected value is? A to b, uniformly distributed. Okay, hold that thought and work this out. Pause the video. Right, hopefully you said, oh, this isn't bad at all. 1 over b minus a is a constant. Right, that guy goes along for the ride. So we have 1 over b minus a times x squared over 2. So we get 1 over 2 times b minus a. And this is going to be b squared minus a squared on top. And we can actually clean this up. We get b plus a times b minus a on top over 2 times b minus a on bottom. Boom, boom. And we get b plus a over 2 or a plus b over 2. I just like to write it in alphabetical order, no difference. The expected value is exactly where we think it should be, which is in the middle. Right, the variance I'm going to leave as an exercise for you guys, but let me just write out some of the details. So we want the variance of x. So let's compute the expected value of x squared. So let me just write out some of this. So we're going to get x cubed over 3. And I'm not going to write everything out. See if you can see how you get from step A to step B. It's going to look like this. And then I always have to look this up. But you can factor difference of 2 cubes. So this factors into this. And then the variance, which I'll leave all the details for you guys, is going to be the expected value of x squared. So this guy, which it looks like will cancel, expected value of x squared minus the expected value of x squared. And then algebra, 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 this is what I'll leave to you guys. You'll get b minus a squared over 12. Okay, so this is just algebra. So in summary then, as an example, let's let x be distributed uniformly. And sometimes people will just write u for uniformly. On the interval 0 to 10, the expected value of x is 0 plus 10 over 2. The variance of x is 10 minus 0 squared over 12. The PDF is going to be 1 over b minus a on the interval 0 to 10. And that's it. All right, as one final example, so that's kind of your concrete example, because it's something that we can wrap our minds around. Let me do another CDF example where it's just some arbitrary PDF, which isn't necessarily modeling anything, and let's see how we can derive the CDF. So example. Let's let f of x equal cx on the interval 0 to 2. Let's say this is PDF. Let's first find C, and second find the CDF. So you're welcome to try one or both parts and pause the video. All right, regardless, let's now do it together. So to find C, well, if this guy's a PDF, then I know that the integral from 0 to 2 of my PDF, that better equal 1. Because I told you it's a PDF, so when we integrate it, we better get 1. So pulling the C out, and then integrating, we get x squared over 2, so I get C times 2 squared, which is 4 over 2. Minus 0 equals 1. So 2c is 1, and c is 1/2. All right, so c is equal to 1/2. Let's come up with the CDF now. Well, we have three scenarios. If x is less than 0, well, the probability of being a number less than 0 is going to be 0. Again, one way to think about it is this is our entire sample space. Another way to think about it is that my PDF values are going to be 0 outside of that. So if I try to, on the left, so if I try to integrate up to that, then I'll get 0. If x is bigger than 2, well, what's the probability of being less than or equal to some value that's bigger than 2? Well, that's going to be 1. Right? The probability of being less than or equal to 3 is equal to 1, for example, because this interval is 0 to 2. So we need to study x in the interval 0 to 2. Okay, so big F of x, by definition, is going to be, again, the probability of being less than or equal to a particular point, which is the integral from negative infinity to that point of f of t dt. F of t, so 1/2 t dt. But since all of my probability is between 0 and 2, then this isn't actually totally correct. This negative infinity shouldn't be negative infinity. The smallest value here should be 0. Because if I were to write this out in terms of fully articulated, then from negative infinity to 0, I'm actually just integrating 0. Then from 0 to x, I'll integrate this guy. Right? Because this fully represents the probability of being less than or equal to x. The challenge here is that my PDF changes. It's not this guy from negative infinity to x. It's this guy only on 0 to 2, and it's 0 otherwise. So this is actually the integral I want to compute. So doing so, I get 1/2 times t squared over 2, integrate from 0 to x, and I get x squared over 4 minus 0. So this is my CDF. As a sanity check, big F of 2 better equal 1, because that's at the upper end of my interval, and it is. 2 squared over 4 is 1. Again, let me show you some of the power of the CDF now that we've computed it. If I said, oh, you know, what's the probability that x is between 0.5 and 1? Well, instead of integrating from 0.5 to 1, we now have just a function that we can evaluate. This is just big F of 1 minus big F of 0.5. This is 1/4 minus 0.5 squared over 4, and we're done. All right, this was an introduction to continuous probability distributions. This is definitely an abstract section. Historically, this section is challenging to students. So don't feel bad if you need to rewind it, watch it again, and ask lots of questions in the discussion. So I hope you enjoyed the lecture, and I will see you next time.